All right. I hope everyone liked the good music and welcome. So, hello everyone. It is with great pleasure that we present to you our vision for the ultimate 3D editor. So, despite the advancements in technology, we believe that the perfect solution doesn't exist yet. That's why we have taken on the challenge to create it. So, our goal is to bring together all the important elements that make a 3D editor truly exceptional, from user-friendly interfaces to advanced features. We want to deliver a product that will revolutionize the way you think and work with 3D data. However, we understand that different users have different needs and preferences. So we would like to hear from you. What else would you like to see in a 3D editor? What features do you think are essential? Because your input is invaluable in helping us create the ultimate editor. And we can't wait to hear your thoughts. With our cutting edge technology, innovative approach, and extensive experience in the field of annotation, we believe that we are the best solution for those looking out to streamline their annotation processes. You can hear? Yeah. So our platform, SuperAnnotate, has been designed from the ground up to make the annotation process as fast, efficient, and accurate as possible. We use cutting-edge algorithms and deep learning techniques to ensure that the results are of the highest quality. The user-friendly interface makes it easy for even those with little to no technical background to use our platform. And of course, our support team is always available to answer any questions you may have. Our commitment to quality has earned us a top spot on G2. It's a leading platform for software reviews, which is a testament to our expertise and effectiveness. With thousands of successful projects completed on behalf of our customers, we have proven a track record of delivering high-quality results, whether you are looking to annotate images, videos, 3D data, or even text. So SuperAnnotate is the ideal solution for you. We are passionate about what we do, and of course, we are dedicated to helping our customers build beautiful models. So for the topic of today, we're going to talk about 3D and types of 3D data with their challenges. So first of all, 3D in deep learning is a very interesting area with a wide range of real-world applications. So, this webinar will provide you an introduction to 3D data representations, computer vision tasks, and challenges that are unique to it. So, 3D data has always been challenging to work with, especially in the AI sphere. But recent advancements in 3D acquisition technology has taken a great leap after the increased availability and affordability of 3D sensors like LiDARs, RGBD cameras, and 3D scanners, and of course, much more. Unlike the widely available 2D data, the 3D data is much richer in scale and geometry and information, thus providing an opportunity for better environment understanding for machines. However, the availability of 3D data is relatively lower, along with a higher acquisition cost as compared to 2D data. Yeah. But before we dive into use cases and its challenges, let us go over some popular types in which 3D data is handled. So the first type of data that I would like to talk about is depth images. Depth images contain the depth values of a scene in the form of distance from the camera to the meters for each pixel the image is in the frame. This depth information from a scene holds immense value for many tasks like self-driving cars, augmented reality, robotics, etc. Such information is very useful for tasks like enabling motion parallax as the camera scans over still scenes and animation in virtual, for example, cameras. But when emphasizing on a particular object in the scene for 3D modeling, this information becomes insufficient and inaccurate at the present state-of-the-art, models. So, and we've seen a lot of cases where people apply or visualize depth images or depth data onto the 2D data and process them as such. But to go to a more pure, 3D data, we have the point clouds, which can come from a LiDAR or radar cameras, for example, and they are an important aspect of 3D representation. They consist of a collection of 3D points that are distributed in a 3D space. Each point has a deterministic position, so they will be you will have your X, Y, and Z coordinates. And they may also have other attributes initially, such as RGB colors, which would also be, having segmented classification of those points. So one of the advantages of point cloud representation is that it preserves more high quality geometric information of the 3D space compared to the depth images, which I just mentioned. And this, high quality information, geometric information, which can be subject to discretization. However, point cloud data also presents some challenges, such as a large degree of freedom and high dimensionality, so which makes it difficult to synthesize the data accurately. But this is where annotation of this data comes. The annotation of the data point cloud becomes critical and can help to complete the data by providing additional information and context, which can be used to more accurately synthesize and process the point cloud data. By incorporating annotation into point cloud data, it becomes possible to extract even more valuable information and insights from the 3D point cloud. Another type is a voxel, which is also known as a volumetric pixel. It is a fundamental element of 3D data representation. It is a direct extension of 2D pixel into a 3D dimensional space. To basically explain it, a voxel is like a pixel, but in 3D. The arrangement and relative proximity of voxels in a 3D grid define the unique structure of the volumetric data. Now, think of a voxel as a quantized point in a three-dimensional space with a fixed size. However, voxel representations are often too sparse and can result in a trade-off between detail and computational resources. For this reason, voxel representations are not always ideal for 3D modeling, which requires more intricate and nuanced data representation. But despite this challenge, voxels still remains an important element in 3D representation and have significant presence in fields such as CV, robotics specifically. And the last one is the polygon mesh, which is a collection of edges, vertices, and faces that together define the shape and the volume of a polyhedral object. The convex polygon faces of the mesh join together to approximate a geometric surface. Similar to a voxel, a mesh can also be regarded as 3D point cloud set sampled from a set of continuous surfaces. Except they have relatively lower complexity when comparing them with a voxel. And here we can also have triangle mesh, a quad mesh, or a convex polygon, which is an n-gon mesh. Approaching a more realistic representation, a mesh can also consist of polygons with holes or concave polygons, depending on your generalizability of your representations. Yes. So why 3D data? So these types of data are an important technology because they enable the creation of first of all, highly accurate 3D maps and modeling of the environment. For example, let's take LiDAR data, which is light detection and ranging. We learned that recently. It uses laser light to measure distances and create detailed representation of the physical world. So including objects and features such as buildings, roads, buildings and features such as building, roads, and trees and topography. This information can be used in a variety of fields, including autonomous vehicles, robotics, geography, and geology, to make better decisions, improve the safety, and of course, increase the efficiency of your models. LiDAR also provides a high-resolution data that can be used to create digital twins. These are basically virtual representation of real-world environments and can be used for simulations and planning purposes. Some use cases like this, maybe you can see them in augmented reality and virtual reality applications. Overall, LiDAR plays a critical role in many industries and is essential for the development of cutting-edge technologies that are transforming our world. Yeah, give me a second. So some of the use cases specifically that we find with 3D data in are, first of all, scene understanding, which we can use the 3D data to better understand complex scenes by performing tasks such as 3D detection, semantic or instance segmentation, depth estimation. This information can be used for applications such as robotics, AR, VR again, and autonomous vehicles, to better understand and interact with the surrounding environment of the objects. And since we are talking about autonomous vehicles, a critical role in the development of autonomous vehicles is providing the information needed to understand and navigate the complex driving scenarios. So LiDAR or in-stereo cameras can be used to collect 3D data of the environment, which can be processed using deep learning models to perform tasks such as object detection, lane detection, and traffic sign recognition. And of course, most importantly, we don't want our models to detect humans as pine cones, as we have seen in some of the models deployed today. In other use cases, for example, a very, recently popular one is smart city. In it, 3D data can be, and deep learning specifically can play a critical role in the development of cities, providing the information needed to make informed decisions and drive innovation. Cities can use the 3D data to understand the urban environment, including infrastructures, assets, and traffic flow, again, which can be used to improve urban planning, development, reduce congestion, and enhance the livability of the city. And the same type of data that smart city works is for the agriculture sphere. So there again, 3D data can be used to precision agriculture to optimize the crop yield, reduce waste. LiDAR and some other remote sensing technologies can be used to collect 3D data of the fields that they usually use them to process and perform such as crop classification, counting the plants, yield prediction. I guess a specific topic that I would love to see more in the future is time series using this data. Again, all of this information can be used to improve the crop management, reduce water usage, and increase efficiency in agriculture. Actually, in our next webinar, we will dive specifically into this topic of agriculture using 3D data. Yeah. So if we go back again to why using 3D data is more advantageous than 2D data, I can give you two examples that I've seen in recently published, again, I guess more or less famous papers. To start with, we can take the remote sensing or focus more specifically on the automatic mapping of individual urban trees, which is actually becoming increasingly important for city management and planning. Although deep learning-based object detection networks are the state of the art in computer vision, their adaptation to individual tree detection in urban areas has been scarcely studied. Some existing works have employed 2D detection networks, as you've seen a lot, for this purpose. However, these have used 3D-dimensional data information only in the form of projected future maps. So they're not really taking advantage of 3D data as a whole, which means they're losing a lot of data. So this specific paper is trying to exploit the full 3D potential, for example, they use an airborne laser scanning point clouds. And by using a 3D neural network for individual tree detection with a data set on an urban topographic ALS point cloud with 10K, I guess 10,000 more or less handed labeled ground truths, trees have proven to achieve an average of 83% precision regarding to the common 0.5 intersection over union criterion, 85% in terms of the stems. 85% in terms of the stems were found correctly with a precision of 88%, while the tree area was covered by the individual tree detection with an F1 accuracy of 92%. What I'm trying to say is that they basically outperformed the traditional delineation baselines and recent detection networks. And they did all of this with a relatively small sized data set. Imagine what you can do with the bigger and more refined data sets. And I guess to cover autonomous driving, another paper use LiDAR, which allows vehicles to see where it's going. The LiDAR system inside of it works by measuring the object's distance relative to the self-driving vehicle's position to create a 3D replica of the environment. An integrated computer system, I guess, measures inside of the car, measures the time between the initial laser pulses and the receiver using the speed of light to compute the distance the light has traveled. So the 3D data emits and computes like data from, I think, like 100,000 lasers pulses every second. It uses this data to form a point cloud, and it gets recreate a 3D model of the surrounding objects. After LiDAR sees the objects, it identifies them. For example, it can be humans, again, vehicles, lanes, and so on, and predicts their behavior to determine the vehicle's reaction. Also, LiDAR data is more consistent during different weather conditions, like it can be day, night, extreme sunlight, or rain, which RGB cameras they're not very consistent in that regard. And overall, will have higher accuracy, giving us more advantages. And of course, depth data received from 2D cameras will never match the accuracy of a 3D LiDAR data. But to summarize the findings of that research, it was clear that using LiDAR camera separately had its own demerits and disadvantages. And that may lead to accident, which is, I guess, in case of autonomous driving, is a big no. So instead of relying on a single sensor, they use multiple sensors, which in their case was like LiDAR, radar, and RGB camera, and combine all of these sources into a single model. Yeah. So in this LiDAR and radar were an active remote sensing where the time delay between the emission and the reflection is measured, and the camera used here acts like a human eye, which is sensitive to light. From these three, LiDAR always had the highest performance and the most accuracy, but the combination of these three collect information from various sources and produce the accurate results to perform the test. Thus, they concluded that a combination of the three is used for autonomous vehicle is a viable and more efficient solution than just relying on a single one. Yep. Give me a second. So why did LiDAR and 3D data more specifically has been improving in the recent years? And there has been a lot of focus on 3D technology in recent years because of its many applications benefits, as I mentioned. The advancement of 3D technology has made it more accessible and affordable. As a result, it has become a critical component in developing of various industries. With the increasing demand of high-resolution 3D mapping and data collection, it has become a key tool in providing the precise and detailed information that is needed to make informed decisions and improve efficiency. Additionally, rapid growth of the autonomous vehicle industry has created a huge demand for 3D technology in general. It provides the critical data needed for safe operating of, again, self-driving cars. The focus on it has also been driven by the need for improved safety and accuracy in various other applications too, as well as the desire to develop new and innovative applications for the technology. With its many benefits and growing demand, it is clear that the focus on this technology will continue in the upcoming years. But with all of the improvements and the advancements of the 3D field, there are still some problems that need to be addressed, for which the first, and I guess the biggest one, is cost. For example, LiDAR sensors and radar sensors are still relatively expensive compared to the 2D cameras, which makes it difficult for widespread adoption in consumer application. Despite the recent advancement in technology and miniaturization of sensors, the cost remains a barrier for many companies looking to incorporate LiDAR into their products and services. This is particularly true for small-sized businesses that may not have the resources to invest in expensive hardware. Another problem is complex data processing and annotation. So 3D data is often difficult to process and interpret, requiring specialized software and expertise to make sense of the information. The data generated by sensors can be large and very complex, which again can also be challenging for companies that lack the necessary computing power and software tools to process it. Especially when you have very complex voxel data, which my computer never is able to process it. And this can result in delays and increased costs associated with the data processing, and of course the added challenge of data annotation. And the last problem that I have identified is the fact that it's still in early development stage. Despite the exciting potential of 3D technology, it's still it's in its early stages of development, and there is a lack of clear regulation and standards in the place. And this can be a challenge for companies looking to develop and commercialize 3D-based products and services. The lack of clear regulation and standards can make it difficult for companies to navigate the market and know what is required of them to bring their products to market. It also makes it challenging for customers to know exactly what they're buying and what to expect in terms of performance and reliability. As the technology continues to evolve and mature, it is extremely important for us that regulations and the standards are put in place to help us guide the development and ensure the safe and effective use of the 3D data in a variety of applications. Now that we have talked about the problems, how are we trying to solve them? Basically, we are trying to make, first of all, 3D data more accessible and overall improving the performance of models by tackling some of the problems previously mentioned. The first would be improving the data accuracy, which is, again, extremely important. So by providing high-quality data annotation services, we can help improve the accuracy and reliability of your LiDAR data or 3D data in general, which is critical for applications, autonomous vehicles, building information modeling. Our platform is designed to support the needs of 3D data users by providing the tools and services they need to achieve high levels of accuracy and reliability in their data, and consequently, you will be able to build the beautiful models. The second will be providing expertise and support. So with years of experience in data annotation against deep learning, SuperAnnotate offers expert support and guidance to help customers make most of their data. Whether they need help with the data processing, annotation, creating pipelines like end-to-end, or just training machine learning models, the SuperAnnotate team is there to provide happily the support that you need to succeed. And the last one, like I mentioned, the perfect tool in our vision doesn't exist yet. This is why we are investing heavily in the development of and improvements of 3D editors, which is, I'm excited to show our tool, which is still in development stage, and we will be, extremely happy, if we can build this perfect tool together. You will have to give me a second to share my screen. So to show you the editor. All right. I hope you can see this screen. Anyone can see it? I think you can. All right, so this is, for example, how a project in our tool would look like. Right now, I only have a single scene for the purpose of, I guess, demonstration. I also didn't have much time to annotate an entire data set. But this is how a project would look like. You can have, you will see your data in your data tab. And of course, your data can always remain on your end. And using integration with hyperscalers, your data can remain on your clouds and your services. Just be rendered on the browser when you click on one of these links. Besides the annotation tool itself, which I will show in a minute, we also have other functionalities, which I guess I can briefly explain. Explore, analytics, and insights are there to provide you extra information about the projects that you're doing, help you query the data set, and basically identify certain use cases, the time that it takes to annotate, or maybe if you find your model is underperforming in specific use cases, visually see why maybe they're underperforming. Because not just you can have the annotations here, but you can also use your model and see how your model is performing visually. So in our use case, we have, it's an autonomous driving, I guess, use case where I have only pedestrians and cars, and yeah, we also have nested classes. So a car can action moving, a human can be occluded, so action moving, and you can also describe what the human is doing, for example. But let's just dive in here into the editor. Yeah, this is a scene of, I guess, again, like I mentioned, autonomous driving, where we can have where we actually have 4 different frames only. And we see, I have done some annotation already. You can see the humans, the cars that are moving. You can choose to, for example, increase the size of the points or their brightness. Maybe change the type of the coloring. So right now we can do it by intensity, but we're also adding, other types of coloring of the cloud points. For example, they can be done by the height of the points, which is very useful in remote sensing, specifically, if it's inside the building, so you can really easily see the walls and the heights, maybe of the objects. You can also, at the same time, you can change the coloring of the vehicles or the humans, pedestrians. I won't dive too deep into like every single functionality and shortcuts, but basically, here, we have a car. When you click on it, when it comes to annotation, if you click on it, it can, show you the sides of the annotation, so you can see it from the top, the side, and the front, which can help you to accurately, pinpoint where the almost pixel perfect annotation. If you choose on this car, it can also show you what's happening to this car across the frames. So right now, you have only 4 frames, but imagine if you had like 100 of frames. You don't want to annotate every single one, one by one. You would love to interpolate in between them. So you can, for example, annotate the first frame, and by deleting over here, yes, we can do interpolation where you annotate the first and the X frame and just interpolate in between. As you may see, in the second frame, the car is way further, and this third frame, it comes back a little bit. So you might say, hey, linear interpolation may not work perfectly in this case. You are right. But we also have some other cases, functionalities. For example, first we can do interpolate, and as you see, it's not perfect, but we can auto annotate it, which will fix the annotation, make sure it's, as you can see, almost pixel perfect. But again, you can, from here, you can mention, like, change the size a little bit from here, for example, from here, or you can also change it from any of the other views, and even with the RGB views. And like I mentioned previously, like not me, but like the paper mentioned, LiDAR data is very good, but combination of, for example, LiDAR and in this case RGB camera would make the the model more accurate and the process more efficient. Yeah, I see that we have a couple of questions, so I guess I'll give you guys a minute or two to write more questions if you have any to ask, and yeah, we can start by answering them. All right, so can we use our own models to speed up the annotation process? Yes, you can. So you can always use the ML or deep models that we have over here to auto annotate the data, but you can also incorporate your own models. You don't have to upload your models, of course. No one likes to share their models or put them online. It's where the money comes. You can upload the annotations, with I guess the LiDAR files that you have, or the RGB files or 3D files that you have. And doing so, instead of doing everything from scratch, your job will be just basically, you can check this view of the first, let's say, car, fix everything. If it's all right, you can go to the next one, and so on. Yeah, let's see what other questions we have. Can you fix existing but not accurate annotations through your platform? Yes, like I mentioned, you can always use your own models, or not just use models to. Sorry. So you don't have to annotate from scratch, but we've seen a lot of cases where people already have their models and they're, for example, performing very well, but not good enough. So what you can have it over here is that you run your models and then you just fix the mistakes of the models, so you can have like maybe 98 or even 100% accuracy. What sorts of, the next question is, what sorts of data formats are you supporting in the 3D editor? This is a good question. I guess it also goes back to one of the problems in the field in general, and that was the standards and regulation. From what I've seen in the field, almost everyone has their own format that they use. And this, I guess, usage of formats is mainly because the cameras are giving you, because you're using the format that the cameras are giving you, for which almost every company that creates those cameras are just giving something a little different. And so there's like no standards, there's like no specific, thing that the industry in general is using. We have the ability to process and accept all of the different type of formats. For example, it can be like PCD files, JSON files, and for the ones that we don't support at the moment, we will be very happy to convert them from pre-processing and post-processing. I guess one thing that I haven't mentioned is that the tool itself can be almost automated. So there is an API functionality for each of the buttons that you see over here, and you can also use this functionality to pre-process, post-process, or I guess process the data in between the annotations too. So for example, you can have your own QA scripts where it runs on the data. So if, for example, it detects an occlusion, you can automatically flag it out and make sure that someone fixes them. Yep. All right, so maybe I can go back to the screen. Share desktop, this one. All right. I guess thank you everyone for joining this session and sticking with me until this time. I know that there's still some other questions that we haven't answered, but please, if you want to see the tool or we want to play around with it, using for not just these use cases, obviously, but for all the other use cases that I've mentioned, please, feel free to reach out to us. And yeah, thanks again for coming.